I'm Arthur Keene. I'm with TigerGraph, and I'm going to talk to you about operationalizing knowledge bases and use as an example swap networks. So I'm going to give you a brief introduction to our company, and I'm going to give you some of the backstory of why I'm interested in this particular area. In 2015, I gave a demonstration and a tutorial to a large bank on the West Coast, and they gave me an education in FIBO and the crash of 2008, and how swaps played a role in the crash, and how you have to be careful about what's happening. If you're in a network, a social network, you have to be careful what's happening 1 hop, 2 hops, and 3 hops away from you in that network. And the person I was talking to challenged me to start working on this problem, and I see him sitting in the front row there. And I knew immediately how to solve the problem, but I didn't have the resources to do it. And I knew because I had worked in reliability prediction, and I'd also worked in transaction analysis, where you look at the cost and profit of transactions in an enterprise, where you drive those costs from the general ledger, which form huge networks that you drive costs through. And I had also used these techniques in cybersecurity to determine who's being attacked, what assets in a company are being attacked, and I applied this to large intrusions that happened, state-run intrusions that happened to the DoD networks in the 2005 and 6 time frame, where contractors were being attacked, bases were being attacked, and we're trying to figure out what the correlation was. Were they attacking a particular weapon system and so on? And I solved that problem by using a technique called an IAC network. Got a patent for it too, but the technique, basically you use an ontology and you map your data to a graph and you propagate some currency through the network and you find hotspots. In the particular case that I was using, I found, for example, that drone technology was what was being attacked from millions and billions of attacks on the network. So what I'm going to do today is walk you through how one would do that with transaction networks in banks. And for those of you that are not with financial services, I'll peel the onion and take you one layer at a time. So first of all, I'm going to look at, not at swaps necessarily, but the aggregation of swaps between banks, which is who trades with who. So one edge between a bank could represent potentially thousands of edges. And then I'll take you one level deeper where we look at between banks, if there's swap contracts, how do you look at that? And then finally, because you're not looking at time when you're looking at swap contracts, look at the swap contract network between banks, where payments are going backwards and forwards between the banks, and looking at risk from that point of view. I'm going to quickly skip through the marketing material that I was given. I'm sure that'll make you very happy. Makes me very happy too. So what I want to tell you about is TigerGraph, and then I'll get into the rest of this, because TigerGraph is what I'm using underneath this. So TigerGraph was built from the ground up to be a native MPP graph engine. It was built over a period of 5 years in stealth. It's both scale up and scale out. To give you statistics, we have a customer in production with a 1 trillion property edge graph. For those of you who are RDF, a 1 trillion property edge graph is several trillion RDF edges. Okay? And that is in production. It is also a scale up system. That particular system is receiving transactions at 2 billion updates per day. That same system is receiving 2.5 queries per second and answering those queries, and those queries involve 10 plus hop deep links into the graph, because it's doing fraud analytics, and fraud is notoriously long hop oriented. And that's kind of the system that we're dealing with here. So it is a system that distributes the traversal of the graph, and hence the speed on the long hops. And the long hop, for example, a 10 plus hop, as I'm describing down there, for this particular customer, we're doing in about 126 milliseconds, and have SLAs on that. So enough about TigerGraph. Let's get into the networks. Boy. So if you could see that, what you would see is a grayed out network of companies and relationships, basically a knowledge graph, okay? And if we look at the relationships that matter, who is controlled by and trades with in that network, this would be like looking at a knowledge graph and picking out the relationships that you want to traverse in the PageRank. The controlled by relationships and the trades by relationships. In this particular example, and this I did in 2015, I'm going to apply the PageRank algorithm to this, but first identify the banks in this network and also identify the bank holding companies. And you can see those here if we had the right colors. So this is a who trades with who network. And Atana showed you an example of that earlier on where he's looking at companies as well. So when we do the who trades with who PageRank, we come up with something like this, and we can look at the most influential or most connected bank in this particular case. But what does it tell you about risk? It tells you the potential of risk in here. It doesn't tell you what could possibly happen. Whether the variable rates go up or down. In 2015, when I did this is actually kind of interesting. I actually had to stitch together different technologies to do this. I actually used OntoText to do the PageRank, converted the results over to Neo4j so that I could use Link Curious to display them. Thankfully today I don't have to do those kinds of things. So this is actually crossing from an RDF graph to a property graph, and which you can do fairly easily. Once I'd worked with who trades with who, I wanted to go a little deeper. And this is hard to read at the moment, but bear with me. What you're seeing over here, if you see these clusters of yellow groupings, are swap contracts. So in the previous diagram, one edge was represented by this whole grouping of swap contracts. You can also see a slightly green line and a slightly green line and a slightly red line. And what those are the payer and receiver sides of the swap. What I realized when I did this is I didn't know which way to orient the PageRank because I didn't know which direction the swaps were going to go. But those are the actual swap transactions because these are actually swap contracts. So this is yet another view, and you can go see this online. The source is The Most Influential Swapper. It's on LinkedIn, and if you download the slides, you'll get the link to it. Part of what's going on here is that the swap transactions are actually a dynamical network. When you have a swap, what you have is a payer party that's going to pay a fixed rate and a receiver party that's going to pay a variable rate based on some nominal amount. That variable rate usually comes from something called LIBOR, and there is a chart underneath that I'm not showing at the moment. So if the LIBOR rate is lower, the payer party will be paying the receiver party. There may be situations where there's no payment, and there may be situations where the payment goes the other way. The point here is this graph is changing, and it's highly dynamic. So the question is, how do you analyze something like this? And how do you analyze something like this where it might have trillions of edges in it? So I started building a capability on top of TigerGraph to do this kind of analysis. And what you'll notice is I've got FIBO coming in. I'm bringing FIBO into TigerGraph. I'm bringing in the LIBOR stream, because those are your variable interest rates. I'm bringing in the legal identifiers along with the parentage of the companies, the ownership and control relationships, and also synthetic swap transactions. And I've also brought in some geospatial information so that I can report by country and region and subregion. So what my goal with this is to run various graph algorithms on this. One being community detection, who are the communities swapping with each other, and the other is PageRank, who's most influential when I look at the dynamics of the system, because this is actually PageRank in time, because the PageRank's going to change as the LIBOR rates change. And the other is building an IAC network where you can go to any bank in the network and see what the risk contribution is from anybody else in the network, which is what I did for the cybersecurity. So first steps here, if you load FIBO, I've highlighted the interest rate swap, and you can see that it has subclasses and superclasses, and this is part of a large, huge ontology that contains hundreds of ontologies. This information is how I intend to communicate what I have in my graph, because after all, this is the de facto way of understanding what these financial terms actually are. However, on the other side of things, I want a computation that's efficient, so I'm going to create a representation that's efficient for those swap computations. I'm having my cake and eating it, not getting slowed down by FIBO, but also creating bespoke representations that are efficient. The LIBOR information is interesting. If you look at the parentage of a company, this particular swap here is 8 layers deep from the swap. Conceptually, if you had a swap on either side, there would be 16 hops away from each other. The potentially very long traversals in this graph. Swaps graph schema. What I'm doing here is I'm creating a bespoke representation for the swaps computations and a representation to bring FIBO in. For those of you that are RDF literate, you'll see that I have statement, predicates, objects, and subjects, and graphs. And I can bring FIBO into that. At the bottom of the picture, I have companies, payer party, receiver parties, and then the swap transactions on the bottom, and the country information on the other side. I can map this information. I take all of FIBO and map it to that representation at the top and load FIBO. And then you'll see various other aspects over here on the right-hand side. The legal identity information is being mapped between the country and company and providing information about the parentage of companies. And then on the left-hand side over here, you have the LIBOR rates coming into the LIBOR vertices and being connected to the swap payments. So this is basically my graph. What you should find interesting about this is that it's a hybrid. In the graph above the page, there are potentially thousands of OWL classes in there. What you see at the bottom is a representation that's custom made for doing this computation. And you see relationships between them. I'm cross-referencing them. So you've probably not seen something like this before. On ingesting that, here's an image of the universe that you're seeing, which is basically the swap event graph. Very, very large graph. Since this is a demo running in PowerPoint, well, not a demo, it's a presentation, I can't show you the actual demonstration, but I can show you some of the routines that were generated for doing these computations. So the calculation you see at the top is the PageRank computation that was generated for that specific schema. This is part of the reason that it's fast. It's getting baked into C++ and running specifically. You'll note that if you look at that PageRank algorithm, from top to bottom, it's 17 lines, of which around about 12 are the actual PageRank logic. So a very efficient algorithm. And a sample below that is how I'm computing the swap positions in the different transactions, also using GSQL. Next, community detection. This again was generated by TigerGraph off of their Louvain community detection template. It was again customized automatically for this particular schema. I can't show you all of this algorithm. It runs about 3 or 4 pages. Not as succinct as the PageRank, unfortunately. But a very efficient algorithm, nevertheless. Finally, the IAC network. What I realized when I first started working with these IAC networks is that they were very much like PageRank except for two things. One is they involved apportionment and weights, and they didn't move links. They moved some currency, whether that currency be the number of attacks in the network or the actual amount being transferred. So for example, if I was doing cost analysis on enterprise transactions, the currency that you're moving is the costs and then also the payments you're receiving through that network. How this works when you set these up is, if you understand the PageRank algorithm, this should be quite straightforward. If you have a transaction going, or a swap event going from a payer to receiver, the impact of these transactions crosses the entire network, going up through the parents, and there's an apportionment to the parents and also to the children and also to siblings over here. So what happens in an IAC network is it operates just like PageRank, except it's going to move and keep these values segregated throughout the entire network, so that when you look at a particular parent, you can see where this information came from, where a particular value came from. So if you look at a particular parent, you can see that there's a contribution to their risk that's coming from a child that might be several steps away. And that's the IAC algorithm. I don't have a picture of that for you, of the code, but certainly can demonstrate that at a later time. So that's it from me now. I can take questions. I think I have a couple of minutes left.
Thank you. Thank you, Arthur. We indeed have time for a few questions.
Thank you very much for this presentation. I just wanted to ask, how do you incorporate the standard, the conventions of the swaps? Because the swaps, like each swap have different conventions. In this like presentation, you mentioned that the purpose is like to show the connections. If beyond that, like if you want to show, for instance, for instance, like giving shock to the system, and then there's like you are gauging the systemic risk, for instance, and then the connections, how they are connected, and the swaps, for instance, legs, like to the semi-annual, or like to the what is the business convention, like to the bad holiday days and all those stuff. Like how do the conventions are incorporated into this framework? Thank you.
I'm not as sophisticated as you describe. I'm using a certain kind of a fixed float interest rate swap with one currency. They're all the same. So I don't have any variation in the swaps at this point. But I'd love to talk to you about how I could bring that into my system. Thank you.
Anyone else?
Did you version the graph at all? So temporally over time to see, as you say, as the floats move, as counterparties move in and out?
It's part of the representation.
Yeah.
Yes. So you can see when these swaps are time-stamped as well. Yes. Yeah. It's not versioned. It's basically I've got everything time-stamped.
Okay. So you have valid from, valid to. You can eventually take a temporal slice at any point to see how it's evolving.
Exactly. And PageRank over time is also a sequence. In fact, one of the things, I'm fairly new to TigerGraph. One of the things I realized is I can actually simplify that representation, because TigerGraph allows you to put time series directly on vertices. And I didn't do that. I probably should simplify it. So for example, I could actually have the time series directly on the swap contracts, and it'd be a much simpler representation. I've just seen that the experts on TigerGraph do that kind of thing. So you can have complex types as properties on a vertex, and that type may be an array of, or a map of actual swap transactions. And that'll be a simplification that I'll bring in as I learn more about building algorithms in TigerGraph itself.